So all of all the workshop scripts for today will be here on the GitHub. And everything should work right if you've downloaded the package from GitHub within the past couple of months. There's one thing that I fixed for tomorrow that you would have to have updated the package in the since last night to work, but most everything, even tomorrow, will work with the recent copy of the package. Nice. So if you just Google CTMM learn, then it should take you to something weird, and then also here. Yeah. All right. So today we're going to talk about modeling and approaches where you don't assume that your sampling schedule is important to your organism. Some kinds of data, for some kinds of data, the best modeling approach is a discrete time model, where the state at the next step is dependent on the past steps. So an example of that would be a population model for a species that reproduces on a set schedule every year. The natural way to model that is my abundance this year depends on my abundance last year and the conditions throughout last year. But for movements, you can move at any time, most of the time. And you do tend to move at any time. And even if you didn't, the way that you sample the data with the GPS collar or tag, that usually has no relationship to whatever schedule the animal's decision making might be on. So while for some processes you would want to use a discrete time model, with movement you almost always want to use a continuous time model. I'll talk more about some confusions about that later. So animal tracking data are complex. This is an example of a wood turtle. Each circle represents a 95% confidence area of where that location, corresponding to where you think the location of the wood turtle might be at that time. At different times, you get different satellite reception. So at some times you have a better location estimate, and at other times you have a worse location estimate because you can see fewer satellites in the sky. And compared to GPS error, which is usually on a scale of 10 meters to 100 meters, wood turtles don't move that much. So you might think this is an impossible data set to work with. So our goals here today, one, we want to account for autocorrelation in the tracking data. So tracking data, I think it's a safe bet that every single data set you have here are temporally autocorrelated, meaning that at one moment in time, wherever the animal is, and then the next time you record their location, they're not that far apart. Right? An independently sampled data set, you would wait so long in between fixes that the animal could be anywhere in their home range with no relationship to that last location. And we're going to account for autocorrelation with stochastic process models. And we're going to account for sampling irregularity and sampling mismatch between different data sets with continuous time models. And if we have to, we'll account for location error. We'll do that with error models that we calibrate the parameters of with calibration data. And we're not going to assume a particular kind of model. We're going to do formal model selection, and then we'll go back and test our assumptions, and we'll see where the weaknesses of our models might be. And as Ellie said yesterday, I would never calculate something where I only gave a point estimate. We'll also estimate our uncertainties as well. It's against my religion to only put a point estimate. And we'll do some population estimation where we'll propagate the individual uncertainties into the population level parameter estimates with hierarchical models. And I always try to reduce the bias and error as much as possible just by working out the estimators, the best estimators I can find, deriving estimators, working out the bias of the estimator, removing that bias if I can. So a lot of the statistical methods you'll use today have possibly several orders of bias removed for you. Okay. So to motivate this, I think the strongest motivation is in home range estimation. So when I say home range, I always mean the range distribution. I always mean home range in the sense that Bert meant home range. So this is a black bear on one of the Great Lakes in North America. And the red dots are the tracking data, and the black contours are 95% coverage area home range estimates. These estimators, they're the same kind of estimator, but there's one assumption that differs. This estimator, they're both kernel density estimators. This one assumes that the data are sampled independently. And when you can see the movement path like this, that's very much not true. And this estimator, it's the same estimator, but instead of the assumption of independence, there's assumption of an autocorrelation structure that is consistent with the kind of paths you see. And this 95% coverage area is about the size of the data that have been recorded. And this 95% coverage area is much larger than the recovered data. And so when I first worked this out and showed this to people, they would say, wrong, that looks good, right? Because like, how can you possibly say all this so far unused area would be included? And I'll also add that there's quite a bit of uncertainty here. These dashed contour lines correspond to the lower and upper limits of what we think the magnitude of the home range area is. So there is about a factor of 2 difference in area between this lower limit and this upper limit, right? And that's just for the magnitude of the area. We don't know exactly where that area will be, but this model says, given the amount of autocorrelation in the data, this animal's probably not going to stay in this area. It's going to keep expanding out into other areas about that scale with a lot of uncertainty. So that was just the first half of the data, though. So I held back the second half of the data to make a point. And the second half of the data is here in kind of orange gold color. And this is supposed to be, in both cases, the 95% coverage area. It is supposed to contain 95% of the bear's locations. That is very much not true here, because the animal did continue to move to other areas. And here, this coverage area is slightly too small. Okay, so One of the things that happens when you ignore non-independence and you use a method that assumes independence when you don't have independence in the data is that you get overconfidence. Your parameter estimates, the confidence intervals are too small. Your predictions are overly optimistic in their precision. And in terms of estimating the space use of an animal, you underestimate space use when you ignore the non-independence. Why does this happen? Does this really happen in practice? Is this a cherry-picked example? And how did we fix this? Are the questions you might be asking. Why does this happen? So I think this is a good kind of example to conjure up with simulated data where you know what the truth is. So this is the same process in both cases. This is a simulated animal that takes about a day to get across its home range. It's the same amount of data in both cases, 100 locations. But here, there's a year of data collected, so there's a couple of days between each fix. So that means the animal crossed its range a couple of times between each fix, which means there's not very much relationship from one fix to the next. So there's not very much autocorrelation. And here, all the data was collected over the period of 1 hour. And it takes the animal a day to cross its range. So it hasn't gotten anywhere in an hour. And I use the same estimator of the animal's home range in both cases, an estimator that assumes the data are independently sampled. And all the estimators you went over yesterday, every one of them, for the home range, for the range distribution, they all assume the data are independently sampled. And in this case, this answer is approximately correct. It's pretty good. And in this case, it's so small you can't see it, but it's there. And it should be biologically obvious that if you think about it, why this came to be wrong, because this little bit of data is not representative of the whole area the animal could use. You don't have a fully representative amount of data there. Okay, so does this happen in practice? Am I inventing things to be afraid of? Unfortunately not. So kernel density estimation, if you want to estimate a distribution of anything, and especially if you're in more than one dimension where histograms don't really work very well, it is the statistically best method for estimating distribution when you don't have a model. So when you don't do what you're going to do on Friday with resource selection functions and step selection functions, when you don't have like a mechanistic model, this is the best statistically known way of estimating a distribution for independently sampled data. And we generalized this to autocorrelated data back in 2015. There's probably several dozen methods for independent data, KDEs. And that's why you see all these names, ad hoc, Gaussian reference function, least squares cross-validation, plug-in. But so far, we did this in 2015, and there's not a second one for autocorrelated. There's just one. I'm sorry. I haven't had any more ideas. Mike Noonan at UBC, we took all the data our collaborators would give us at the time for range-resident individuals, non-migratory individuals, which was a couple dozen species and hundreds of individuals. And we did the same cross-validation that I showed you with the black bear. And we did every method that people typically use. So everything you saw yesterday, sans the Brownian bridge, because that's a different thing, it's an occurrence distribution, all the range distribution estimators. And we found, depending just empirically across these data sets, depending on which one of those methods you use, on average, you get a home range area that's 2 to 20 times too small. So over here is like Gaussian reference function, on average 2 times too small. Over here is like K-loco and least squares cross-validation, closer to 20 times too small. They perform very badly on autocorrelated data. So here's just kind of a summary of those results for 95% coverage areas and 50% coverage areas, which is something that people estimate less, but is easier to cross-validate because it's not close to 100%. And it's not the case that these estimated, when you use a stochastic process model, it's not that you're just making a giant area. Just, it's doing better because it's bigger. It's not that it's bigger. It's not too big on average. It's slightly too small on average, if anything. And the biggest, other than the method you use, the biggest predictor of how, what that negative bias is going to be is the effective sample size. How long did you track the animal compared to how long it takes to cross its home range? So if you track it and it crosses its home range about 4,000 times, you can pretty much use whatever you want, pretty much. But if you only tracked it and it crossed its range 100 times, some of these methods are pretty bad. And if you only get 10 crossings, then you really have to account for the autocorrelation. And this is a slightly older method. We have a couple of improvements. And you can get down with the slight improvements we've made, and then if you do bootstrapping on top of that, you can get down to about 2 or 3 home range crossings and actually estimate something that's not very biased. It'll be around here in terms of the bias. And then after 4 bias corrections, and I'm out of ideas. I can't help you beyond you got to have 2 or 3 crossings. I'm sorry. And empirically speaking, because of the scaling between body mass and home range size and home range crossing and how big of a battery you can put on their neck, the bias is worse for larger species. So those of you with little animals that cross the range all the time, really fast, and you get lots of home range crossings, you're over in hundreds to thousands, and you might be okay. And those with larger species, you can be really bad, especially giraffes and elephants. So how do we fix this? Stochastic process models of the autocorrelation. So I just took an accepted method, an accepted KDE method, and I just took that assumption of independence, and I dropped it, and I redid the math. So now let's assume an autocorrelation model. And then we'll talk about where the autocorrelation model comes from as well. So autocorrelation in your tracking data, when you can see a really well-resolved path, you have lots of autocorrelation. So these are the time lags from one point to the next. And this is the correlation between every 2 points, this time lag apart. And here it's about 100%. So if you have a track that looks like this, your autocorrelation is pretty much 100% for many, many time lags, almost 100%. And oftentimes we don't have the method we want. Oftentimes you want some fancy method that has this and this and this, and it just doesn't exist. So you have to make do. And if you want to use a method that assumes independence, you thin your data until you meet that assumption. And you start thinning your data, and the autocorrelation goes down. And if you can still here you can still barely see some of the track, and the autocorrelation is still really high, like 90-something% at one lag. And by the time you have no significance, one time lag out, this is, for what you saw to begin with, this is how much data you'd have to thin down to. So, and then on the other hand, what if you're not interested in home range estimation? What if your species is not range resonant? What if it's dispersing or migrating, or you're just interested in other quantities? Then what about speed estimation with these data? How good are these data at speed estimation? Pretty bad, right? All right, so for speed estimation, you'd want this. That would be really good data for speed estimation. Yeah, so you might have to work with the data, or there might be better methods sometimes. So data sets like this, which 30 years ago, if you just went out in the field and VHF tracked something every week or so, this would be a very common data set. Really convenient for home range analysis because there's this whole statistical literature on kernel density estimation that you can rely on, and the assumptions are probably being met. Worthless for speed and distance estimation. And then a data set like this becomes inconvenient for older home range methods, but is great for speed and distance estimation. So, my objective is I want to make methods that can handle whatever autocorrelation there is in the data. And if you have a data set like this, do a home range estimate and it's okay, you don't have to thin the data. And if you have a data set like this, you'll see what we get when you stick this in later. Okay? You can put it into a speed estimation. We'll see what happens. Why use a continuous time method? Like I said, there are some biological processes where the most convenient model is a discrete time model. But for animal movement, that's generally not the case. So there are examples where you might want discrete states, like the flower that a butterfly moves between. A very good model for that might be discrete states, but it's very unlikely that the butterfly will take those steps every 10 minutes on the clock, Or an example I've seen more recently, fruit bats going from fruit tree to fruit tree. A discrete model for the trees where they go might be very appropriate, but it's extremely unlikely that that will correspond to a discrete time schedule. Or like Ellie's example yesterday, the anteater, discrete behavioral states for resting and then moving might be very appropriate, but it's extremely unlikely that those transitions will happen on some regular interval that you measure with your collar or tag. So at least for movement ecology, you almost always want, maybe not a fully discrete state, but a discrete time process. Excuse me, a continuous time process. Maybe not a continuous state, but a continuous time process. So I think we went over this some, but an example of a continuous time versus discrete time, just to reiterate this. So step lengths, turn angles, where you assume, as you do in a hidden Markov model, like with a momentum package, where you assume these transitions happen regularly, let's say on the hour if you sample once per hour. This would be a discrete time process. And here's the transition from one continuous state to the next. And in a continuous time model, for the discrete time model, this is it. Right? The animal just goes here to here on this schedule. There's nothing interesting in between. Whereas for animal movement, the in-between is probably not straight lines, right? Straight between, and the decision process was probably not when we collected fixes, right? And a continuous time model, you don't model with just a transition from one fix to the next. You just assume there's some continuous trajectory that goes between the data points. You don't know what it is. So what you get is a distribution of possible trajectories that are consistent with the data, which looks something like this. And on average, they are around the truth. So the advantages you get for movement ecology is that your sampling can now be irregular in time. So what? Missing some data points. Some of these Paul Cross's buffalo data we've been using, the sampling interval grows slowly and then it shrinks slowly. That's okay, doesn't matter. The sampling schedules can differ across individuals. That's fine as well. And this is because the parameters are independent of the sampling schedule. So in a discrete time model, that time step is an important parameter of the model. And like I said, there are processes where that is like the most appropriate approach, like a population dynamics model with the species that they only reproduce this season every year or so. Like that 1 year interval might be very biologically meaningful. But for us, as far as the true process goes, that's just something we programmed in our collar or our tag. It's not really meaningful. And discrete time models can be intrinsically scale dependent. Bjorn might talk some about this on Friday. But so with the continuous time model, whether you apply the model on 2-hour data or on 1-hour data, it's the same model. But in a discrete time model, if you construct a model with 2-hour data, if you construct a model with 1-hour data, those are not equivalent models. If you take the 1-hour data model and you marginalize every other time, it's not equivalent to the 2-hour model. It's a different model. So for movement, because movement can happen at any time, and generally, continuous time models are more realistic and they have a wider scope of inference. So you can more easily model temporal and spatial scales that are very different. They can span orders of magnitude, and you can calculate things that come from first semester calculus, speed, distance, acceleration, power, and energy. These things all come from time derivatives. In a discrete time process, there is no time derivative because it's not continuously defined in time. You have to have a function that's continuous in time to have a derivative. So these things are only truly meaningful in a continuous time model. And this is not specific to continuous time, but this is specific to models that aren't super nonlinear, like correlated random walks. But if you don't have these super nonlinear models, the location error is very easy to model. So terrestrial people, for some reason, really love these. But then you go into marine people, and their discrete time models are linear. So their discrete time models can handle location error very easily. Whereas the terrestrial people's models, You know, they love correlated random walks, and it's very hard to put location error in a correlated random walk. So you saw what happens when you neglect autocorrelation home range estimation, which Anesh will talk more about. And then there's also the problem of neglecting autocorrelation, in speed and distance estimation. I hinted at that a little bit before, but there's also a bias problem. And you guys talked about on Monday, especially, that your straight line distance speed estimator, you know, distance divided by time, the thing you learn in middle school in the US, I don't know what they call that here. So the one that doesn't have the derivative, before you've learned calculus, that estimator, you get different estimates with different sampling schedules. So that's also a problem of your model is not using that autocorrelation to estimate the speeds like it could be. So you want to get the same speed estimate with coarser data as you get with finer data. And let's say there's no location error, or the location error is very insubstantial. This method, which this is what we've learned so far because we're climbing the ladder of lies. If I estimate speed with straight line distance, is it going to be overestimated or underestimated? Underestimated, because a straight line is, what's special about straight lines? Yeah, it's the shortest path. So anything real that is different from a straight line is a longer path. So when you coarse in the data, let's say there's no location error, your speed estimates are too small. And then we'll talk about what location error does later. Okay, so the building block continuous time stochastic process models. So I'm going to go back over this today just to talk about their parameters. So independent locations. On the left here, in all these examples, this is a real African buffalo from Paul Cross's data set. And on the right is a set of simulated data that are independently sampled from a process that is as close to this as possible, but it doesn't have any autocorrelation in it. So you can see the difference between the real data set, 1 hour buffalo track, and this simulated data set. And this is the assumption of independence. This is what it looks like. This is what you assume with all of yesterday's home range estimators. This is what you assume with classical resource selection functions, a variety of other methods. So that's the assumption. Yep. And then next, Brownian motion, same buffalo. And this is a simulated process with Brownian motion that has the same, an estimated diffusion rate that's very close to what the buffalo's is. So this is no longer teleporting around. Now there's a finite diffusion rate. But two things you might notice that are quite different. One is that the simulated buffalo is gone. It doesn't have a home range. There's nothing constraining it. And the second thing is that, at least for 1 hour buffalo data, this is very jittery. All right? And that's because Brownian motion doesn't have a speed. It doesn't have a velocity. It doesn't even have a heading or a bearing. Its motion is fractal. Between every 2 times, if you try to trace out the path for Brownian motion, the path length of that path is fractal and has an infinite distance. For coarse data, good, that's fine for coarse data. because trying to say that there's some, straightish path between 2 points, when you can't see that in the data, it's a parameter that you're just making up, basically. And Ornstein-Uhlenbeck motion adds one parameter, which is a spatial constraining parameter. So this is starting to look quite a bit like the real buffalo, and that it's going to stay in an area, but it's still very jittery. So the real buffalo has this persistence of motion to it. And that, at least with 1 hour data, you can just kind of barely, almost all the time, resolve what the buffalo's speed is. Whereas this Ornstein-Uhlenbeck process, it still has fractal motion. It doesn't have a finite speed yet. So these are all the kind of building block, continuous time stochastic process models that you would find in the literature used for movement ecology. Here's the integrated Ornstein-Uhlenbeck process. It differs from Brownian motion in a different way, and that now you can see that this has a smoother motion to it. So this process, you can estimate speed with this process. So the motion is very smooth, but it doesn't have a spatial constraint. This will diffuse forever. So this doesn't have a home range. And that's what you find in Devin Johnson's crawl package. And the last basic model will have, is one that has all the properties of the last two models. So it has persistence of motion, it has a finite speed, and it stays within an area, right? And at least for me, there's still one thing that I can see in the data that is still not there. I don't know if you guys can see it though. Do you see any? I can see one last thing. Yeah. So the buffalo move about twice as much when the sun is up than when the sun is down. So there's a non-stationarity in this data that the activity is different when the sun's up than when the sun's down. And if you put that in there, it looks pretty good, just without any spatial context as well. Yeah. So going back to Michael Noonan's comparative analysis paper, what we saw empirically, even though this is the most common assumption and methods used on tracking data, that in our data sets, less than 1% of the data sets met this assumption. And it was really one data set, and it was a coyote, and the sampling was like once a week. And then less than, at least at that time, less than 30% of data sets looked like Brownian motion or Ornstein-Uhlenbeck motion, in that you couldn't resolve finite speeds in the data set. So this is very coarse data, and this is like moderately coarse data. And most data sets, about 70%, you could see that the speed is finite. There's a signature of that in the data. And you would need that to explain all the autocorrelation in the data if you weren't going to thin the data down. Okay, so those are simple models. They're stationary models. The behavior is the same over time. So something that's like coming soon, here's a continuous time model that's a little bit more realistic. This is similar to the models, the hidden Markov models you were doing yesterday. but it's a continuous time behavioral switching model. So this individual has two states that it can transition between, and it can transition between a moving state and a rest state at any time. And those times don't have to correspond to when we sampled the data. And right now, there's no R package that you can do that in. If you want to do it, you'll have to look how Tio did it, and he has his own MCMC code, and you would have to do it that way. But this is something, we'll have this in an easy to use package probably within the next year or two. So we're behind discrete time methods because the math for the discrete time method is, I want to say easy, but it's relatively very easy, but then the math to do this gets really hard. So there will always be cool things you can do with discrete time methods that you will not have a continuous time analog for, just because we'll always be behind because the math is so much harder. And the other thing we're going to do with our models is we're not going to assume our model. We're not going to, today, we're not going to base a method off of a specific model. We're going to try a whole bunch of models, and we're going to select the model that looks the best, or that performs the best and looks the best. Okay. So now the file you want to be on the workshop scripts is this intro file, and you want to download this whole package. And after you've done that, you want to be in that working in either having had loaded the package or in the working directory of the package so that you can pull the data. And this is what it should look like at the beginning, the CTMM intro script. Do you guys need a couple minutes? Okay. Any questions?
Just one question. Is there any?
Oh.
Was just a quick question about if the PowerPoint presentation was already loaded to take notes directly on it, or?
I can upload it.
Thank you.
Sorry.
No, it just helps.
Yeah. Is everybody ready? Good? Wait? Good? Okay. So in the continuous time movement modeling package, there's help files for every function. There's several vignettes. There's frequently asked questions. There is, if you have questions after these 2 weeks, there's an online user forum that you can use. There's a GitHub with issue reporting. All these scripts, you know where they are now. All the manuscripts I keep on a permanent Dropbox. So all the methods, if you want to know what's behind them, there's papers for all that. And then if you want to know what's new in an update, there's that as well. Sometimes people, they want like a newsletter, and I tell them that's in the package. Every package has a has the option of having a news file. Not every package maintains that. But Okay, so if you load the library, the first function you'll use will be the function for importing either CSVs from MoveBank or Move objects or Move to objects. I think that's in there too. And if you're in MoveBank format or Move format, you should be okay. The object structure, here, we'll see. So here's some a MoveBank of the Buffalo data. This data is also in the package. There's a bunch of data in the package. I think these are all the data sets in the package. These are 6 Buffalo in a list. Everything in the CTMM, if there's multiple of them, they're just in a regular list. And each of these, after they're imported from a MoveBank CSV or a Move object, they're a telemetry object in the CTMM package. And it's kind of the same as a Move object, except there's a lot of extra structure on things related to velocity and location error. But it's a data frame at its heart. It's not complicated other than that structure. Yeah, so the Buffalo data set, if you run summary on them, they're mostly collected at 1 hour, except Pepper. This caller had a malfunction that you'll see when Anesh talks. Various numbers of months in this roughly the same area. So for plotting the tracking data and for plotting the distributions you estimate, there's built-in functions for that. If you just plot the Buffalo data, this is what you'll get, the 6 Buffalo. If you give them a rainbow of colors to separate them, here they are. There is a color function in the package which has a bunch of kind of useful things in it. One of them here is to color by individual. So this uses an algorithm that what it does is it makes more separation in the colors where there is less separation in space. And you don't have to use a rainbow, you can use something else. It just has to be a function made in the right way that makes colors. And so here, these 3 Buffalo are together and it gave them RGB. And these 3 Buffalo are together and it gave them CMY. And that's automated. There's documentation on that function. There's a bunch of options here on how you can color something. This is just kind of for visualizing things. So Martina talked about this a little bit. The default projection when you import data into CTMM is a 2-point azimuthal equidistant projection, which, so you always want to have a projection that's locally flat and minimizes distortions where you are. So this is a projection that if you have a big continental or global migration between 2 points, this projection is fairly safe even there, assuming the 2 points get identified with the geometric, the two medians, the 2 geometric medians clustering algorithms, assuming it gets those 2 points, which you could also put in by hand. That's pretty safe in that every distance from those 2 foci are correct. They're not distorted. If you just have an animal in one area, then I'll talk about that in a second. First, let me plot which way is north. So this annoys some people. This is just, there are proj arguments to rotate the projection. I could preserve north up, but the last time I checked, the projection functions in R that I was using ignored those arguments. And it was always one foci here, one foci here. I can check again in a couple of years, but if that bugs you, if you don't have a big continental or global migrant, the 1-point azimuthal equidistant projection is also automated with the median function, the CTMM median function. And that will calculate the geometric median, just k equals 1 geometric median, no clustering. And both of these are using, it's a k medians clustering. So both of them are using the median, which is robust to outliers. So you could have a couple points that are like on the other side of the globe, and it would be fine. You would get the same, basically the same projection. It's robust to outliers. So this is the 1-point azimuthal equidistant projection. And that's what it looks like. It preserves north equals up. And here, this is fine. This is only, 100 kilometers across. This is okay. This is not going to be very distorted. You don't want to use like a UTM projection from like a couple of zones away. That would be really bad. Okay, now we're going to talk about looking at the autocorrelation structure in the data. So the data set we're going to use is Scylla. Here's what she looks like in this north equals up projection. You can color by time. That's really simple, but very useful for seeing like dispersals and migrations and things, which is good when you're going to do home range estimation. You really need to be sure that, like, does this animal really have a home range? Like, if it's dispersing, it doesn't, at least not during dispersing. So going from red to blue or vice versa, you can see that this animal went back and forth a couple times. It's not red over here and blue over here. That would be like, that doesn't look like a resonant settled animal. And the estimator we look at to look at our autocorrelation structure is called a variogram. A variogram is an estimator of the semivariance function. It is different. You have looked at something similar probably with the R's ACF function. R's ACF function is called a correlogram, and a correlogram is an estimator of the ACF, the autocorrelation function. So the difference is the ACF function is upside down, and it starts at 1. And so why don't we use the ACF? Well, the ACF, we'll use it in a minute actually, but it is for when you're not supposed to have autocorrelation and you want to ask, do I have autocorrelation that's not supposed to be there? That's what the ACF's for. The variogram's for, I've got autocorrelation, I want to see what kind do I have. This is unbiased. The ACF, when you do have autocorrelation, because you're not supposed to, it is not unbiased for estimating the autocorrelation. It's good for testing whether or not you have autocorrelation, with the assumption being that you don't. So they're almost the same, but slightly different with different purposes. There's a help file with lots of options. We'll use at least one of those options. There's a vignette. And one thing I will point out in the vignette, which maybe for a couple of you is important, is if you have sampling intervals where you collected data and you're like, okay, this month is 2-hour data and that month is 5-hour data. Some people do that. I don't recommend it, but if you do, we can turn this variogram with the default arguments into this nice looking variogram with arguments that account for the fact that you did that. This is only visual though. When you go to fit the models, if you did that, it doesn't matter. The models are continuous time models. They don't care if you switch your sampling rate up and down. It's fine. But for visualizing, if you want to see like what's in my data, that does make things a little difficult. So one option, which you can't use with really big data sets, is the option for more accurate confidence intervals. So the naive algorithm from the geostats literature is O of n cubed, which means that if you double the amount of data, it is 8 times slower. I got that down to O of n squared log n. So you double the data, it's 4 times slower. That's good enough for thousands of locations, but it's too slow for millions of locations. Here's what it looks like. In the beginning, it's about the same as the fast algorithm that is not right. But as you get further out in time lag, there are differences. This gives you a much better sense of what the autocorrelation structure is as you go out in lags. So what is this? Now that we have a better picture of it. So on the x-axis is time lag. This is not the absolute time. This is not when you started tracking. And this is not 1 month after you started tracking. This is 1 month between any 2 data points. So you go through the track 1 month apart. This is all those data points. 1 month apart, what do they look like? And this is the semivariance, and it's what's the square distance you get after moving for 1 month, proportionally. I say proportionally because we fix it so that this asymptote is the variance, the location variance of the process. So if the location variance is 23 square kilometers, right? After if you wait a year for the buffalo to move around, right? Since there's no relationship between these points after a year, it's just whatever the actual variance is. Right? So this asymptote, for a range resident animal, the variogram should asymptote to the variance of the process. But then when you have a lot of autocorrelation, that means that I wait some amount of time and I don't get that far. If I wait a tiny fraction of a month, I'm not going to get but so far away from one fix to the next. So the asymptote here, this looks okay as far as an asymptote. By default, we only plot the first half of the variogram because the second half of the variogram, in terms of its ability to estimate, it gets worse and worse until it's completely worthless. This is when there's only, by the time you're at the very end, there's only 1 pair of data points, beginning and the end. So like statistically, you can't estimate anything with 1 data point. So this is junk, and then it gets, we plot here just by convention. This is kind of messy, very noisy. And if you zoom way in, here. So if we had Brownian motion, we would have a line forever. You would just get farther and farther away the longer you wait on average. You would have a line. And if we zoom in even more, you deviate from Brownian motion and you have an initial quadratic cusp here. And what that means is you can see in this data that the buffalo has a finite speed. Brownian motion does not have finite speed. It has infinite speed. And so it would go straight all the way in. And in the data, you would never see any paths, like smooth paths, like this. You'd always see it's always jittery. So one thing you can see when you have finely sampled data and you can estimate speed and distance is that you can see these smooth paths in the data and you see this initial curvature in the variogram. And then if the animal is range resident, you can see the asymptote of the variogram corresponding to the variance or the spread of the process. All right. And how long it takes for this to asymptote? Oh, a question? Yeah, feel free to ask questions at any point.
So, sorry, I might be jumping ahead,
No.
but if you have like a range resident individual that disperses, how might this variogram change?
You'll see, usually with like one dispersal, is there a marker here? Yeah. There we go. I mean, one, when you have your scatter plot and you color it, you'll see it'll be red in one area and then blue in another area or something. That's one thing you see. And in the variogram, is that? You'll see it'll, at short time lags, it'll be going to the variance. If it disperses from one area to another, in this specific case, at short time lags, most of the time, it's in one area or it's in the other area. There are a few times where it's trends, when it's going between. And you'll see this, but then at long time lags, you're going from one area to the other. And you'll see it'll go like this for about how long it stays in each area, and then it'll jump up again like that. And on the XY plot, so this is the time, that's the variogram plot. On the XY plot, this corresponds to one area, and the other area's variance being here, and then this larger variance that includes the two being here. That's what it'll look like. Got another question?
Yeah, so you said that you print about 50% of that variogram. So
By default,
by
yeah.
default, do you recommend that we only look at the 50% to determine range residency? Or
I
would you ever-
recommend that looking at the other half of the variogram is at your own risk.
What if we have really finely sampled data?
That doesn't help.
Okay. So just try to base it off that.
The
first
finely
50%.
sampled data gives you more detail here, but it doesn't help anything further out. And there's a question behind you.
Just to extend this diagram, so if you had a seasonal migration, would your variogram go back down again? So for an annual cycle?
Yeah, so if you have a yearly migration, you will see the big variance that includes both summer and winter range. And then on a yearly scale, it'll come all the way back down. Because from one time to 1 year later, I'm actually not that far. And yeah, it'll come all the way back down. Yeah.
But you need 2 years data to get 1 year. But if we're using the first 50%,
Yeah, you wouldn't see it in the
want like
first.
a 2 year
You'd have
track.
to zoom out.
yeah,
But if you zoomed out, you would see it come back down. Yeah.
Cool.
And if you had 2 years of data, you'd see it do it twice. Is that it? Okay. Yeah, feel free to ask questions with any of this material. All right. So when you're doing like GLMs or something, you don't have to worry about initial parameter estimates because either the formulas for the parameter estimates are worked out exactly, or there's this Newton-Fisher algorithm that can converge on the correct parameter estimates from like anywhere, any initial guess basically. So here, it's a little more complicated when you have like your own model. When you have your own model, it's not like a canned statistical method, like a GLM, and you're doing likelihood optimization or you're doing MCMC, you're doing Bayesian stuff. You want to have a good initial guesses of the parameter estimates. So there's a function for that you'll call before fitting. So here's the function called interactively. So in RStudio, you'll have this gear icon. And in addition to the zoom bar, we now have a little sliders. You don't have to do this. This is for learning. Okay, you're not going to have to do this every animal. Okay, we're just learning right now. So the first one is for the variance. And like I said, the asymptote of the variogram is the variance. So we can make it bigger. We can make it smaller, right? And the default is 99.9% of the time pretty good. And then we have our position autocorrelation time scale. We can make that longer. So now it takes longer for the variogram to asymptote. This means that it takes longer for the buffalo to cross its home range. This means that it takes longer for the data points, the location data, to become independent. We'd have to thin even more to use a method that assumes independence. Or we can make it very short, right? So the animal's crossing its home range faster, the locations are independent and less time lag. And we can also play with the velocity autocorrelation time scale. If it's longer, that means that the animal tends to go in bouts of ballistic-ish motion at the same speed for longer. And if it's shorter, the animal tends to have less correlation in the velocities. And if it's zero, it's like Brownian motion, it's a line. Okay. You could do this manually, maybe a couple times to get a sense of a feel for things. But most of the time, you would call it non-interactively, and it's just going to take its guesses and store them. And then we're going to fit a bunch of models and do model selection with C2M select. So what it's going to do is it's going to fit, you're going to put in the guess object, and it's going to fit a model with all those parameters, and then it's going to pare those parameters down. And then it's going to do model selection on all those candidate models. And because you're not doing like a GLM where you can do like Newton-Fisher optimization, you have to do like more general optimization. It takes a little while. The algorithm that it's using is O of n, linear in the data. If you have twice as much data, it will only take twice as long. So you can, if you think things are taking a long time, you can take like a small subset of data and you can extrapolate out how long is this going to take for everything. It's also, you probably have multiple individuals tracked. So that's an embarrassingly parallelizable computation. You can, if you have 8 cores on your processor, you can safely calculate 7 of those at once. So it's slower than like a GLM, but it's not really slow in the grand scheme of things. Okay, I'll stop that. I've already done this. Uh-oh. Uh-oh, I overwrote this with the wrong file. Crap. Okay. I just realized, yep, I can't stop that. Because I wrote another file named Scylla.rda. It's not the same thing. I'll have to fix this. So this is a great time for questions and a break, because this is going to take a minute. And I apologize. It won't take forever, but it'll take like a couple minutes.
This is probably skipping ahead too, but
No problem.
if we're looking at the variograms of our individuals and we see that they're range resident, so they can have a home range, is there a way to speed it up to where we can only fit the ones with home range is for the models? Like,
What
do
do
we
you-
have to fit like all of them? Like say all of our individuals are not independent. Like, do we still have to fit that independent model?
Are they like in a herd or something?
No, but if we like look at the variograms and we can see
That
that.
they're similar? I mean, so you want to fit them all individually. And you could use one's fit as the initial guess for another, but it's probably not going to be much better than the guess, the automated guess.
Okay, so it's better just to run each individual.
Yeah. And we don't currently in the package have models for animals moving together in a correlated way. And that's because I'm waiting on getting the behavioral switching models first. Because I find in practice, at least with things that you guys put tags on, you're typically pretty efficient. And what you put tags on, the animals don't tend to stay together forever. There's some like fission fusion. And because if they stay together forever, you wouldn't waste 2 tags or 3 tags on this group of animals. It's always together. So we need the behavioral switching models in place. And then we'll put in the correlated movement models for animals that are sometimes like male elephants or something, where they're together sometimes and sometimes they're not.
So in this behavioral switching model, it always goes between 2 different states, or do you define how many states, or like how it works? Because
It's the same as what you guys did yesterday, except it's in continuous time. It's exactly the same, except one of them is a discrete time. So the movement is discrete from one time to the next, and the behavioral state switching is discrete. This time I'm in this state, I might switch to 1 different states at the next time. And the continuous time behavioral switching models, you're in a state at a certain time, which means maybe you're moving a lot or you're not moving a lot. And then every time there's a small probability that you could switch to another state at any time. And that doesn't have to have any correspondence to your fix, your sampling. So it's mathematically more complicated because from one fix to the next, there's an infinite number of times where you could have switched states. So the math is way harder to do for the continuous time behavioral switching, which is why right now, if you want to do that, you got to do it in Bayesian MCMC like Teo did and published. Let's see. I think this is the last one. So this is likelihood maximization with an extra debiasing based on Rimmel, if you've ever heard of that. But it's not exactly Rimmel. because it turns out Rimmel doesn't work in continuous time correctly. So it's a custom method that is, the bias is pretty low. And if you don't have location error on, which most of you might not need, you only have to optimize 2 parameters in these models, the 2 timescales. But if you turn on location error, then you have to model 4 more parameters. So it'll take 3 times longer. Unless you have Argos data, which has the error ellipses, then wait, it's more than 3 times longer, because then, I can't remember. I think I worked this out for Johannes at some point. You have to use a higher dimensional. It's quite a bit slower. It's still linear in time. It's quite a bit slower because you have to use a higher dimensional Kalman filter, and because you have to estimate more parameters. You have to optimize more parameters. So there's a lot of math done to minimize the optimization of parameters. A lot of the parameters are worked out by hand. And the slowest is if you have Argos data with the error ellipses, because then you have to use the highest dimensional Kalman filter and estimate a whole bunch of parameters. So that's a few times slower. But mostly when people have Argos data, they don't have a ton of data, so it's not a big deal. Those of you that will be the slowest are those of you that have like really high frequency data. And then with high frequency data, you almost always need a location error model, because most of the information on movement, say from one time to the next second, most of that's location error, not actually your animal moving. So yeah, it's still linear in time, but there's a higher dimensional Kalman filter and more parameters that you have to numerically optimize. Okay. So here are the candidate models that were attempted on Scylla. Yeah. Well, let me make this bigger too.
Thank you. Sorry, is it normal, just by running it as well, I have different values of numbers of parallel function evaluations?
Different number of likelihood evaluations?
Yeah. No,
Yeah, that's normal.
That's normal that I have.
Yeah.
I mean, some of them are exactly the same.
Yeah,
Some are
that's
different. Okay.
normal, because so there's a custom. What I quickly found, so when you do this like likelihood based statistics and you have to do optimization, the optimizers in R are not great, and they weren't working for me. Like there were cases where like it's clear this is not the optimum. So I made my own optimizer, and it's very efficient given how precise it is. I mean, R's optim will often finish faster, but it's like not near the optimum, or not as close to the optimum. So mine there is an element of stochasticity to the optimizer, and that it's like randomly changing bases at each step. So it can take slightly longer in some cases, but if there's like one optimum that your initial guess is near to, we should all get to that same optimum within the numerical error tolerance that's set. So these numbers should be the same to within like 5 or 6 digits or so. I can't remember the exact numbers, but when you optimize the likelihood to so many digits, then that ensures that, I think that means your parameter estimates are good to like half that many digits or something. There's relationships, and it's very conservative, the default settings. 4 to 5? Yeah. Okay, so we're going to add IID models that were never attempted. So the model selection here never attempted the IID model, and that's because, you guys must have really good eyeballs. So the ID model was never attempted because when you start OUF, and then you attempt simpler models, so the OU models, when you drop the velocity autocorrelation time scale, and AIC goes up by 1,500. And OU little f is when you can't resolve the two time scales, velocity and position, which is the case for, like, say, short bursts of central place forager behavior, because they're just going out from the nest and back or so. And those two time scales are basically the same. And so AIC went way up, and so it stopped. It never attempted the model of independence. But we can include those. And that's how long they take to run. Right? They don't take long at all. So when you use methods that assume independence, it's that much faster.
Can you tell me what the area means in the summary?
Yes,
What
I
is
will.
that area?
Did you have?
Well, it said, yeah.
Oh, yeah. Yeah. So I just mentioned the AIC. This is not important when we have a stationary mean model, so ignore this column. This column is the effective sample size. Let's run summary one more time before. And then I'll tell you. There we go. So now, when we drop both autocorrelation timescales, our AIC goes up by 38,000. And these two models, anisotropic and not, or isotropic, that's a circular covariance or an elliptical covariance. So here, there is a fair amount of support for an elongated distribution, even in the IID model. Okay, so again, ignore this column. This column here is the effective sample size for estimating area. So in the IID model, it is the amount of data that you have, -1, for estimating the mean, 3,526. With the selected model, it's 18. With the selected model, as far as estimating area is concerned, you might as well have 18 independent data points. All right, you might as well have gone out 18 times throughout this period and gotten a fix on the buffalo and gone home. Okay. So let's look at the individual models. This is the IID and isotropic model. As far as estimating the mean, we have all the data points. As far as estimating the area, we lose 1 degree of freedom. Nothing in estimating diffusion, nothing in estimating speed. No information in that, assuming this model is true. And then we have our Gaussian area. This is not our good KDE home range area. This is a Gaussian area estimate. And here's that estimate, 367 square kilometers with very narrow confidence intervals because we have a very large number of degrees of freedom in the data for that. Assuming that all assumes that model is true.
Can I ask another question?
Yes?
So you were saying during the lecture part in your slides that
Yeah.
if you have a really high effective sample size, that
Yeah.
you can pretty much use
Yeah.
any home range estimate
Yeah.
that you want. So what
Here it was
number?
18
Yeah.
with the selected model.
But if it's like thousands,
It's thousands, it's whatever, yeah. You can be lazy.
Yeah.
Yeah. That's why physicists are so bad at statistics, because they have so much data. So here's a plot of the data and that model. And it's a Gaussian distribution in blue. And this is the 95% Gaussian coverage area. And here's the confidence intervals on the magnitude of that area. Very, very precise, because you assume you have 3,000 independent data points. And if we compare the varograms, here's how they compare. This is our empirical variogram calculated from the data with the good confidence intervals. And then the IID one assumes that if you're any time lag apart, you could be anywhere else in the home range. And so you jump right up to the variance. So, and then here's the confidence intervals on that. They're very tight because we assume we have lots of independently sampled data. So when we zoom in, there's all this white space between the model prediction, and the empirical estimate that's non-parametric, doesn't assume a model. So all this white space is bad. When you see a lot of white space, your model is not capturing the autocorrelation structure in your data. That's not to say that if you don't see any white space, the model's perfect, because this is only time lag. There's also non-stationarity. This is only the stationary aspect of the autocorrelation and whether or not that's being captured. We can calculate residuals, and we can plot the residuals in a scatter plot. And it'll take a little while because it's also plotting the null distribution for the residuals. There we go. So the residuals, if they're good here, are supposed to be independently sampled, or excuse me, independent and normal with a variance of 1. So does this look like a normal distribution? No, there's so much structure here. And all this structure is a huge difference from a normal distribution. And we can look at the ACF, the parallelogram. And again, the parallelogram is for testing. You're not supposed to have non-independence. You're not supposed to have autocorrelation. And you're testing, do we go outside of this dashed line? Do we have autocorrelation? And we're not supposed to. And for the first 12 days, more than the first 12 days, many, many, many lags, we have very significant autocorrelation. You want to go, boop, you want to go right here and then noisy. If this is 95%, you want noisy every 1 in 20 jump out here, right? It's not what we see. Very bad model. So again, the first model is the selected model, which is the OUF anisotropic model. Okay, so here, effective sample size for the mean dropped down to 10, for the area 18. But look what we found though. The autocorrelation, it doesn't just steal information from you, it's really just moving information from one set of parameters to another. Now we have all this information on diffusion rates, and we have all this information on speed that we didn't have before. So this is our Gaussian area estimate. It is a little bit bigger, and the confidence intervals are way wider, right? This is more than double. The upper limit's more than double the lower limit. So we're very uncertain about the home range areas, the size of the home range area of this buffalo. The home range crossing time scale, right? About a week with lots of uncertainty. The velocity autocorrelation time scale on average, because this is a one-state model, right? There's no rest state and active state. It's just a simple one-state model. On average, it's about 40 minutes. This is the Gaussian root mean square speed. This is a proxy for your regular notion of speed, but it's not quite the same thing. On average again, moving active and resting, 14 kilometers per day, and the diffusion rate, the initial diffusion rate, 5 square kilometers per day, with a lot more precision on those last two parameter estimates, because for estimating fine scale data, since this is hourly buffalo data, this is a very good data set for estimating fine scale things as compared to estimating coarse scale things, because we only have months of data and it takes a week for the buffalo to get across its home range. So for this data set, if you run summary on this data set, the sampling period is 5 months, which I put here. One of two things is going to happen to you if you do a lot of movement analysis. One, you're going to memorize all these weird numbers, like how many seconds there are in a day. Or I made a nice little function to do that for you. So everything internally in CTMM is in SI units. And this function turns anything into SI units or vice versa. So that many months divided by that home range crossing time scale, which was about a week, that many days. And we'll see what we get. So this is roughly how many times the buffalo crossed the home range, 19. That number is going to be, oops. That number is going to be roughly your effective sample size, your degrees of freedom for estimating the area. So we got 18 point something, this is 19 point something. So just from knowing how long it takes to cross the home range and how much data you collected, you know roughly how good your home range area estimate's going to be. Okay. Yes? I ran, where's the,
Sorry, my question was, how did you find out how long it takes to cross the home range?
yeah, so, that's just the, back when I ran summary, that's just the position autocorrelation timescale. That's where I pulled that number from.
Okay.
It's roughly how long the animal takes to cross the home range. It's roughly the time to independence. You can make it a little more precise than that, but that's how you should think about that parameter. Let's see. So here, if I plot the anisotropic Gaussian model, we'll see the difference. It is the main difference. It's a little bit bigger, and the uncertainty is much, much larger. Again, this area in the lower limit is less than half of this area, upper limit. Our eyeballs are not, we're not good at comparing areas, humans. So like to most of us, this does not look like less than half of this. I think that's safe to say. But it is, it's less than half. And the second model was the OUF isotropic model. And it's just gonna look basically the same but circular. So it has 2 fewer parameters than the other model. Okay. And we look at the varigrams. They are much improved. Not perfect, but much improved. And RStudio is a little buggy. Sometimes the little gear doesn't come up, and then you run it again and it does. All right. So we zoom in, zoom in, zoom in, and so, all right. They're consistent. It's not perfect, but yeah, it's got some curvature. It's okay. Really, it's less about is it perfect or is it, can you do better? You got a better alternative. All right, residuals. We can look at the residuals. Okay, so that. What about that? Yeah, much better, much more like a normal distribution. Right? And we can calculate a parallelogram, and we can look this, yeah. This is the parallelogram. This is the ACF. It is much, much better. Let's see. So we zoom way in, and first time lag's not significant. Next 3 time lags, they are significant, but look at the autocorrelation, 6%. What was it before 2, 3, 4 time lags out? It's like 100%, right? So huge improvement in how much autocorrelation is left in the residuals after with this model. And then not significant. And then just, like the normal amount of like the 5% you'd imagine they're gonna stick out after a while. So now, if I take, let's see, if I take, these initial guess, and I look at the OU model where I just turn off the velocity autocorrelation, I can make a model that looks pretty much as good as the OUF model, except like right here, right? Everywhere else except like right here, this model looks pretty good. Right. So you might think that's what you're gonna get when you fit this OU model to the data. What did we actually get when we fit the OU model to the data? It's awful. It's not as good as we could have done by hand. Well, look at that. Look at the huge white gap there. That's bad. You see a lot of white, it's bad. And it's clearly not asymptoting at the correct rate. It's taking too long for this OU buffalo to cross its home range compared to the real buffalo. So what's going on? This is, autocorrelation has all kinds of dangers. This is one of them. At short time lags, this is Brownian motion, it's just diffusion. And the actual buffalo at short time lags is ballistic motion. It's continuous velocity. So this model is fitting Brownian motion to a finite speed with a diffusion rate to a finite speed buffalo that kind of moves in the same direction at the same speed. So it's a mismatch here. It's fitting a line to a quadratic, right? Because the confidence intervals are very narrow here and they get wider. So it's really fitting a line to a quadratic, to the initial part of a quadratic. And when it does that, it throws the whole thing off, right? It throws off, right? You could have fit it by hand better than maximum likelihood because the model's wrong. Okay. So here's a little teaser. I simulated a buffalo from our selected model. So it's pretty much the same as the real buffalo without any spatial context. And instead of like not moving much at night and moving more during the day, it's just kind of the average all the time. Right? Those are the main differences. And now I'm going to plot that buffalo. What areas does this buffalo, this simulated buffalo, like? And what areas does this buffalo not like? Does this buffalo like this area? Yes or no? No. Does this buffalo like this area? Yes or no? Yes? Okay, so we all agree. The buffalo likes this area. The buffalo doesn't like this area. Now I'm plotting that simulation with the Gaussian distribution, which is the truth for this buffalo. Buffalo likes this area. It's blue. Buffalo likes this area. Buffalo likes this area, all this area. This area, no, not really. It's okay. This area, All right, so when we just look at a scatter plot and we see 3,000 data points, we assume so much significance, 3,000 data points worth of significance. But in terms of the coarse scale inferences, how many data points should we be thinking in our head when we look at this? 18. If you'd have seen 18 data points, you wouldn't have said what you just said. You would have been like, I don't know, it's just 18 data points. I can't tell. Okay. So take questions and then coffee break. Yes. Where's the mic?
Can you tell me what the difference between that Gaussian area is and like a home range estimate?
And yes, so this is the Gaussian area is parametric. The assumption is the true model is Gaussian. It's not. The kernel density estimate that Anesh will go over after the break, it is a non-parametric estimate. You don't have to know what the truth is. The more data you collect, it will converge on the truth. It could be some weird shape. It's fine. So it's better. Almost always better. The one exception I would say, if you have really tiny effective sample sizes, maybe you should not think about home range areas and just think about variance estimates. Because in that case, the variance estimate is just a better parameter to estimate than the home range area. But it's okay. I mean, there's lots of debiasing in the methods now. There's a very narrow data collection regime where you might consider limiting yourself in what parameters you consider. Yeah.
Sorry, I'm just struggling a second on, we say these are the real location that we have in, well, they are simulated, but let's consider them real. And well, the Gaussian range is telling us that, yeah, actually the buffalo should prefer that area there, but in reality is not using it.
You've only collected 18 data points, so you just got to wait.
Yeah,
We'll get there.
okay.
Yeah.
Right.
Yeah, so, and the uncertainty should reflect that. Like, if I plot this, with the confidence intervals on there, their width should correspond to the size of that area, basically. Yeah. I mean, see this uncertainty? It's about this size. So the autocorrelation model says we haven't collected enough data to really see what the full home range area is. And you don't exactly know. There's some remaining area probably. You don't exactly know where it's going to be, but it's going to be, this is the uncertainty. And this is about the size it'll be, whatnot.
Can you also tell us that? Can you also tell us that there is an avoidance of that area?
In this case, there is no reason. In this case, it's just random chance that the buffalo hasn't gotten around there. So, you know, in reality, you could have, it could be that it's just random chance that the animal hasn't gotten there, or it could be actual selection that the animal doesn't want to go there. And, you know, with this size of uncertainty and with no spatial context, you don't have any spatial predictors yet. With this simple of a model, you can't tell that yet. Friday, we'll work our way to trying to answer that question. Can we say that there's selection in this area is maybe less suitable than another area? But these models are too stupid to really know quite yet.
So far, these models are still having some problem with the autocorrelation that exists on the points. Or is not the effect of the autocorrelation that is giving these kind of like dumb estimates?
I mean, this model explains almost all the autocorrelation in the buffalo data. When I showed you the correlogram,
Yes.
like there was very little residual autocorrelation left.
So it is something else that is outside of the autocorrelation that is having that difference between the simulated points where the buffalo is and what the
No,
estimates are
this
giving.
simulation's good.
Yes, that's what I mean. Like,
It's our thinking that's wrong.
yeah,
We're wrong.
That's what I mean. Like, it's
Yeah.
not fitted to the simulation. It's just like a general probability of being in that space.
So this Gaussian here is the true long-term space use of this simulated buffalo. If I simulate way more times into the future, it will asymptotically give you this distribution. The buffalo will get here. And over time, the buffalo will be here as much as it is here.
Okay.
It'll fill out.
I was just thinking about some of the considerations around working with multiple individuals with different tracking durations and so on and so forth. So if you wanted to compare across individuals and say you had about 100 individuals all tracked for varying durations, how would you go about estimating the home range? Would you do it? Could you compare them?
Yeah, so as long as, let me give you the case where you can't do that first. The case where you can't do that is that you track different seasons and the individuals they live in different areas in different seasons. Right, then you would only want to compare within season. But let's say that's not the case. let's say over these tracking durations, these animals, these individuals are all range resident, yeah, it's fine. You can do that. That's when you use a continuous time model, they don't have to be sampled the same way. And then when you estimate your uncertainties, the animals that you track longer will have smaller uncertainties than the animals that you didn't track as long. And then when we go after Anesh, probably after lunch, when we go to do the population level inference, we'll use a hierarchical model and we'll propagate those individual uncertainties into our population level estimates. So it'll be fine that we resolve some of the home range areas better than we resolved others. All right, coffee time.